Okay, so my project was on ultrasound-assisted fractionation of bio-oils to better improve characterization of them. So, bio-oils are currently being investigated as a greener option for fossil fuels. However, they are very complex mixtures, so when you try to analyze and characterize them, just as the whole sample, it has a lot of, sometimes there's aggregation, there's a lot of chemical shielding, and a lot of other things at play that prevent you from seeing everything in that sample. So, fractionation can separate these samples into smaller pieces so we're able to characterize them and tell what is fully in all of these samples. So to do this, samples are run through ultrasound-assisted fractionation, where a bio-oil is washed with a solvent and then sonicated. And by sonicating, we are maximizing solvent extraction while minimizing sample loss without worrying about degrading our sample. This allows us to pull out everything in that sample that is soluble in that solvent and take out what that wash dissolved, dry out that solvent, and that leaves us with a fraction. So by doing that, you can see in the picture off to the right, you can see the wash being pulled out and it's darker. Initially, the wash is a clear liquid, so you can see if something was pulled out, and off to the picture on the left, you can see the fractions. We don't trust that just one wash is going to pull everything out, so we do 10 additional washes, so 11 washes in all of each solvent. And you can see we use 3 different solvents to give us fractions 1, 2, and 3. Everything that is insoluble, the residual left over, is called fraction 4. And we also run whole sample just to see by comparison if we did learn more. And it's really interesting because these were all dried and then diluted to the same concentration of methanol. So even just visually, we're able to see that these are very different compounds, very different things. And to analyze all of these samples, we use many different techniques that are outlined in this purple table here, but really what we wanted to do was see if we could read all of the molecular formulas in these fractions. So we used the 9.4 Tesla ion cyclotron resonance to read molecular formulas, and we use that for APPI and APCI, which are ionization methods that read more in the non-polar species. And we also ran the ESI, which is a more polar ionization method on the 21 Tesla ICR. And this allowed us to see many different versions. You can see in these charts here some separation of those compounds that we were able to read in the samples. And we wanted to also run HPLC, which is a method that separates samples as they're run through to further separate those fractions and see how they behave. So based on all of that data, we came to a few conclusions. In fact, we did see more molecular formulas assigned in the fractions than just the whole sample. So it seems the fractionation was successful. However, when we looked at APPI and APCI data, they were very similar, which makes sense. They were both non-polar ionization methods. And since APPI was more stable and more compatible with the samples, that seems to be the go-to. But running that in tandem with ESI, which gives us those more polar species, has allowed us to see much more. So running those two together is a good option. And even if samples on the ICR data showed they were similar, HPLC data showed that they had differences, which suggests isomeric differentiation. So they might be the same atoms, but structurally different, so they behave differently. So this project still has a lot to go. There's a lot of different directions this could go in, and this will be ongoing. And I just wanted to say a big thank you to the ICR lab for having me this summer. Thank you.